With this, I'd like to welcome you to today's webinar on heat stress and Earth observation data. My name is Guido Riembauer from Mondialis, and I'm here today with my colleagues Victoria de Andra Brunn and Lennart Meine. And today we want to give you a brief overview of what can be done with Earth observation data, physical model data, and in the context of heat stress mapping. What can we map on heat and heat stress, and how does it affect cities, countries, and the human body? So short overview over the webinar structure. First of all, we will talk about data sources, mainly differentiating between thermal remote sensing, so satellite-based observations, and model-based climate data. These are two different kinds that all have their strengths and limitations, and methods and indices that can be calculated based on these data sets and what we can do with them. We'll then show our application example from a countrywide heat stress mapping before we go into the outlook. Maybe one note on the term heat stress. In this webinar, we focus on the effect of heat on the human body and the use of heat stress mapping in the health or public health context. So heat stress can also, of course, be experienced by other biomes. It can be experienced by vegetation, for example. And this would be a slightly different approach than what we show today. So today is about heat and its effect on the human body and how this can be mapped. So to introduce ourselves briefly, we are Mondialis. We are an Earth observation and remote sensing company from Bonn in Germany. And we focus on open data and open source software. So we mainly use open data such as Copernicus data, aerial surveys that are open data, and also partially high resolution satellite observations. And we make use of exclusively open source software. And if applicable, or if it's possible and okay with our customers, we also try to publish our developments as open source code to contribute to the community. We offer a wide range of services, as I said, especially focusing on Copernicus data and products derived from that, and also high resolution, such as soil seeding mapping. And we also have a strong history in time series and land surface temperature monitoring, which is also connected to today's webinar. Here we have a diverse team with different backgrounds of physics, biology, geography, geodetics, and have been developing a strong AI application focus in the past years. Okay, that's about enough from us. Let's talk about heat. First of all, we distinguish between satellite-based Earth observation data, which directly measures surface properties such as land surface temperature, and model-based climate data. These are model-derived climate products, and they are constrained by observations and provide spatially and temporally consistent atmospheric variables. So these are different things, and I'd like to show the strength and limitations of these, and also addressing a bit on local measurements and context and exposure data later on. So first, what is thermal remote sensing? Thermal remote sensing measures the temperature of the Earth's surface from space. It does so using multispectral sensors that you might know. For example, Landsat is a very prominent example. Sentinel-2, for example, does not have a thermal band. So some multispectral imaging sensors that are on satellites do carry thermal instruments. And if we look at the electromagnetic spectrum here, we won't go into too much detail here, but just to show you that the visible part of the electromagnetic spectrum, which is what most high resolution sensors cover, is really just a very small bit here. And yeah, it goes from violet to red, basically. And then what most multispectral sensors do have on top of that is a bit of infrared. So especially the high resolution sensors usually do have visible light bands and at least one infrared band in the near infrared region. So they usually have some bands in the near infrared or shortwave infrared region, which is very applicable if you look at vegetation and vegetation vitality, health, calculation of NDVI, and so forth. So this is applicable by a lot of sensors, but the thermal radiation from the Earth's surface, this takes place at a different electromagnetic wavelength that is much, much longer. So this is in the long wave infrared, around 10 micrometers, 10 to 12. So only a few satellites carry instruments that can access this. And what it measures is thermal radiation that is emitted from the Earth's surfaces, and you can use formulas to turn that into a temperature value. So you end up with a land surface temperature value that is not air temperature. Obviously, it's connected to air temperature above it, but it's something different at its core because, yeah, you see on the right-hand side an example of the city of Wuhan in China. This is a Landsat thermal image, or Landsat thermal image converted to land surface temperature. And this is just one temporal spot. So this is one day in July, one acquisition. And you see that the range of the temperature values is very large. The lowest values go to 16 degrees and Celsius, and the highest up to 55. So this is not the same as air temperature, which would be a much smaller range here. But this is a realistic example because in inner cities with a lot of concrete, for example, this stuff does heat up. And so surface temperatures like this are also normal for example, Middle European German cities in the summer. You easily get land surface temperatures of about 40 degrees. So what's the advantage of using this technique to map surface temperature? Obviously, you see it has a rather high spatial resolution. In this image, you can differentiate between different city blocks and parts of the city. You can see islands of lower temperature, which are most likely connected to green urban spaces. So you can use this to monitor the effect of green areas on inner city temperatures. So the resolution here at Landsat is 30 meters. It's actually 100 meters, but it's upscaled to 30 meters in this case. And it's a direct observation. That means that it's not a model behind it with model inaccuracies. Of course, you have some inaccuracies because you transform the thermal value into a temperature value, but it's still a direct observation from that day on that spot on the Earth. On the drawback is, I mentioned you don't have direct information on air temperature, so you can't really quantify how hot it really is for a person there, but you get this spatial granularity. It's more of a qualitative measure that you can derive from here. The main limitation, however, is that you require cloud-free observations because, yeah, even with this long wavelengths, you can't see through clouds. You would need radar for that. And that means that you get an irregular or sparse temporal sampling. So you don't have a dense time series. You only get imagery when the satellite flies over and when it's cloud-free. So you can't rely on having a dense, consistent time series here. What data can you use for that? I mentioned Landsat already. It's the most known example. Currently active are the sensors 8 and 9 with a resolution of 100 meter, which can be resampled to 30 meters using the other Landsat bands. And combined, they have a revisit time of 8 days already, which is quite high. By the way, all these data sets that we show here are publicly available and open data, so free to use. EcoStress is another interesting sensor because this one is attached to the International Space Station. It has a similar resolution of 70 meters, even a bit better than Landsat. And being attached to the ISS, it gives you variable acquisition times because it depends on when the ISS is flying above, and this is not as regular as monitoring satellites would do. So you would get different times in a day, and you would get different times between acquisitions, which can be an advantage, and it is or a disadvantage depending on your use case. In this example, also you see the city of Madrid this time acquired by the EcoStress sensors, also showing that yeah, you can see really nice the different parts of the city, the airport, and how this heats up and how green spaces cool it down again. And then you have low resolution sensors. So these are just examples, of course, like MODIS and Sentinel-3, which operate at much lower resolutions, like 1 kilometer, for example. But the advantage then is that you get a global daily coverage, of course, unless it's cloudy, but you get a much more consistent time series. Depending on the scale of the analysis, this can also be a valuable data source. So thermal satellite imagery is great for mapping temperature differences at high resolution and small scales, but they don't provide direct air temperature or other meteorological values. So for that, we would require model-based climate data. And models provide us with a consistent time series that, for example, show how heat evolves over time and how temporal patterns during a heat wave can develop. So these are they model-based or reanalysis data. They describe atmospheric conditions continuously in space and time. And they are called reanalysis data because behind it all, it's a physical model. And this is calibrated and validated using observational data. So for example, even satellite measurements, but also local ground measurements. So it's not directly measured at every location because it's just a model behind it, but you do get a physically consistent data set everywhere on the entire globe with high regular temporal resolution. On the right-hand side, you see the ERA 5 example, which is the most known climate or model-based climate data set that is used, which I will also talk about in a minute. And you see it's really just one point in time for the entire globe available, but of course then at lower resolutions. So the great strength of this data set is that you get a lot of different meteorological variables. You don't only get the air temperature, and this time air, not surface temperature. You also get stuff like wind speed, humidity, rainfall, precipitation, and so forth. And again, it's hourly data with consistent global coverage. So you can analyze when are peaks in air temperature during the day, and how do these variables evolve over time. And yeah, the limitations are obviously that it's much lower resolution than the satellite measurements because it's always at least 1 kilometer, mostly more. So it's not suitable for inner city analysis, but more for large scale applications. And it's a physical model. So there are more inaccuracies inherent than with direct observations. There are several data sets that you can use. I just show two here. Again, ERA 5 is the most known one. This one is available via the Copernicus Climate Data Store. It's an European product by the ECMWF and Copernicus and has a resolution of 1 to 30 kilometers. This depends on what data product you actually choose because at its core, it's hourly data, but there's different types of spatial and temporal aggregations available. And yeah, this one also has this huge variety of different meteorological variables. This, of course, only covers the past. So ERA 5 usually is available with a latency of 1 week, more or less. So you get imagery or data from the last week, but back to the beginning of the 20th century, actually. Whereas if you're interested in forecast, so in the future, then there's also comparable product. It's from the global forecast system. So this is a US based and developed data product. So this provides also global gridded data on different meteorological variables in a 3-hourly temporal resolution up to 16 days forecast. And these resolutions get coarser and coarser the more you go into the future. And also the spatial resolution is not as high as with ERA 5 because it's around 25 to 28 kilometers. But of course, if you're interested in forecast systems, this would be a data set to start with. Okay, just to cover this part briefly, because to have it complete, Local measurements are, of course, a very relevant, but a data source, because with local measurements, we know very precisely what happens at a few points, but not everywhere. So we get very accurate measurements of different meteorological variables, but only at specific locations, of course. So they are used to calibrate and validate modeled and thermal remote sensing data. So they are very valuable, but they are not suitable for large area coverage. So for countrywide analysis or even inner city analysis, unless, of course, there's a dense sensor network deployed. So for example, in a smart city context, some municipalities do deploy these sensors at a very high density. And this would allow, of course, then similar analysis or give a higher accuracy to a potential interpolation of the data. And finally, there's context and exposure data. So this means heat stress can only be experienced if there are actually people experiencing heat stress and not only the temperature there. So heat stress depends not only on temperature, but also on who is exposed. So we need basically data on in risk management, you would call them assets. So in this case, on the people living there. So valuable data sets include population density, as you see on the right-hand side in the Cologne-Bonn region. This is world pop data that is also open data. Very valuable is, of course, age distribution information from census data, if available, because then you can distinguish different age groups and focus the analysis on vulnerable groups, socioeconomic indicators, and also further information on sealing degree and green infrastructure, so land cover data, basically, to help refine the analysis. Okay, now let's talk about what methods and indices exist. Again, these are just examples that we're showing today. The first one would be urban heat island identification. That is a method that is suitable for thermal remote sensing, which I showed in the beginning with the Landsat example. So this helps to locate the heat hotspots, actually. Again, you don't get a quantitative measure, really. It's really just a relative index. So there are various ways and various indices that map your urban heat islands, but the general idea behind them is the same everywhere. The idea is that you define reference areas in rural surroundings around the city, and you take the land surface temperature from these areas, and compare this temperature with the pixels of your inner city. So with this, you get a very good, a relative index with high spatial accuracy and high spatial resolution, showing you the relative strength of heat and urban heat island hotspots. However, if we really want to model the effect of heat on the human body, then a way to go would be thermal comfort indices. And what these are is that the goal of the thermal comfort indices is to grade thermal stress and take into account more variables to really realistically model the effect of heat on the human body. So, for example, wind does have a cooling effect, or it makes a difference whether or not you're standing in direct sunlight or if it's just diffuse sunlight, even if the air temperature around you is the same. Because the body experiences the heat differently based on these variables, or the combination of them. And of course, if we need those variables, then we have to use the model-based data or local measurements even. But if we want to map a large coverage, then model-based data is the best data source here. And we'll just show two examples of indices. One is the mean radiant temperature. This one represents the average temperature of all surrounding surfaces that radiate to the human body. So it really doesn't just take into account the the surface temperature or even the direct radiation from the sun, but also all other radiation fluxes, which means there's different variables involved, as you can see in the diagram, or different streams and radiation fluxes and angles. And also this one does reflect whether or not the person is standing in direct or diffuse sunlight or in the shade. And yeah, it's really just a measure to combine all the thermal radiations that affect the human body. And a even more complex or integrative index is the Universal Thermal Climate Index, the UTCI. Lennart will also talk about this one more, in a minute, so I won't take up too much time here, but this is a really more comprehensive value index because it takes into account more variables. As you can see, it is also based on the mean radiant temperature, but on the bottom of the diagram, you also see it takes into account, for example, the humidity and the wind speed as well, to really model, and even a clothing factor, by the way, to really model the experienced degrees Celsius, so the experienced heat. So you end up with a scale like this. The UTCI values actually are in degrees Celsius, but they are, experienced degrees Celsius, so to speak. And then there are stress categories defined to them. So what you can easily do with this one is that you can look at the heat wave, look at the temporal data, and analyze how intense it is by, for example, looking at how many consecutive days with strong heat stress you had, and then you get a very good indication of the strength of this heat wave. All these indices, here's just a hint on how to calculate them. There are open source software libraries available. In this case here, we use the PyThermal Comfort package. That's a Python package that is freely available and helps to calculate these indices. Yeah, and this is an example of how we brought this on the large scale on a countrywide application, but I will hand over to Lennart for this one.
All right, yeah. Thank you, Guido. Yeah, good morning from my side as well. I would like to show you just one example of how we use or how Earth observation in general is becoming more increasingly important for strengthening public health systems. And we brought one real world application, if you will, that we are currently developing, which is an EO information system for heat stress risk assessment in Pakistan. And yeah, Guido already mentioned it. We are using the UTCI for this, and what we need for this is at first a basic set of climate variables to help to assess the heat stress. And what we are using here is mainly the daily temperatures, maximum, minimum, and mean temperatures, for example, then the total precipitation, relative humidity, wind speed, and the radiation. And we aggregate these all to continuous countrywide raster layers in a very high resolution of 1 by 1 kilometer, and they are based on the ERA5 dataset that Guido introduced before. So some of them are already delivered by Copernicus directly, but others we have to derive, such as the relative humidity or the wind speeds. And this ERA5 data is generally produced in a very dense hourly time series. So the variables are, we have to aggregate them actually to calculate the useful base indicators for the heat stress assessment, and also to just reduce the enormous size of those data sets. So these rasters by themselves, they can be pretty valuable for climate insights, for public health monitoring, probably for example, enabling the assessment of environmental conditions, etc., that contribute to heat stress and climate sensitive health risks. And they also form the database for the calculation for the UTCI, or the Universal Thermal Climate Index, which is a very important indicator for us. So on the next slide, this is a slide about the UTCI. It's an established metric to assess those kinds of heat stress on the on humans, and it's a bioclimatic index for describing the uh, physiological comfort or discomfort on the human body under specific conditions based on the, yeah, as I said before, the ambient temperature, humidity, radiation, and wind speeds. So the heat stress does not depend only on the air temperature alone, but it's induced by the exposure of the human body to numerous or all those conditions. And this results in a field-like temperature, as Guido said before. So we see this scale here on the right side. We have like 10 categories that are ranging from extreme heat stress to extreme cold stress. And in the middle here, you can see just one map of, I think this is from July 24 for a day, just to see where, yeah, the heat stress is the highest in the country. You see it's pretty strong heat stress actually, but in the northern mountainous regions, we have no thermal stress, for example. So this is first overview about, for a countrywide assessment. Yeah, and we see that this product, yeah, it can support monitoring of heat-related health risks for potentially vulnerable groups. So this UTCI, we calculated for, yeah, as I said, on for daily values from the climatic variables I mentioned before, and we use a, yeah, polynomial regression model from the PyLib. And this can then approximate the complex heat exchange between the human body and the environment. And here for this example, on the national level, we have the spatial resolution of 1 by 1 kilometer and a temporal resolution of 1 day. So we have per year 365 grids for the study area. So next slide, please. Yeah, and here just shown as an example, you can see 1 grid per month for the last year, just to see how the heat stress changes over the year for the whole country of Pakistan. And yeah, these grids, they, yeah, what we experience is they can really provide an opportunity to identify areas that have historically been the most affected in order to give them then special consideration in the future, for example, for adaptation measures or maybe for an early information on for the affected population. So yeah, now you can ask yourself, how can this be used just to, yeah, to prepare this vulnerable populations that I mentioned? And that's on the next slide. There is an example of what we are doing with this. So our idea is to integrate these climatic data sets shown before with information on the population and especially in this case with vulnerable groups. So yeah, particularly affected by heat stress are mostly elderly, pregnant women, young children, but also people with chronic illnesses like heart diseases or metabolic disorders of some kind. So by developing these heat stress risk maps, we want to, yeah, to identify these high risk zones where people are affected. So they will offer just a visual tool that translate these, yeah, rather complex EO data into actionable information for the managing, yeah, just for managing these climate-induced health risks for health experts or non-EO experts. So what we do, we are integrating the aforementioned UTCI with the population counts for once, but as well as demographic data on age structure, sex structure, or as well in this case with health data where available. So this is always a little tricky to just to get this data, but if we have it, we can put it into these risk maps. So and shown here on this map, there's a first like simple classification based on the combination of the UTCI and the population density. With this has a resolution of 100 by 100 meter because it's using the world pop, the free world pop dataset on population counts. And this is actually the metropolitan region of Karachi in Pakistan that we see here. Yeah, so we see, or in discussion with our partners, we see that these maps can really be useful for long-term urban planning and also to urgent crisis response. So just helping to fill the gap between the data insights and the practical solutions addressing the challenges of climate change. And also this can just add some insights into understanding the impacts of rising temperatures and heat episodes for vulnerable groups. So on the next slide, there is some, so as I said, we are currently developing this. So we are currently in the refinement process where we actually look what we can achieve by looking at the duration of the heat events. So we have heat waves that we are looking at. We look at the duration of days or consecutive days with higher heat stress. So we weight this UTCI. And on the next slide, you can see the effect that it has. So if there's just one day, we add like 0.1 to the UTCI, in 2 days 0.2, etc. And by incorporating this temporal element, it really can refine the analysis on the affected populations. And that's currently work in progress, but that's what we are currently working on. So those are the heat stress risk maps. And on the next slide, I think that's already our outlook for today. So what we are thinking about here, especially looking at the audience today, we were thinking, what can we do or what can we do to achieve more on a smaller scale and to support maybe the needs of cities and municipalities. We are currently looking into the integration of the urban heat island mapping that Guido introduced before, and also the thermal comfort index monitoring. And also we are looking at more or simpler thermal comfort indices, because the UTCI is pretty complex and takes a lot of climate variables into account, but there are also a little simpler indices like the wet bulb temperature or discomfort index that we can calculate. And this, because it's easier to process, it's faster, and maybe even we could achieve a higher resolution temporal or spatial with these kinds of indices. And the idea here is also to integrate, or what we are currently also doing, just to incorporate land cover data or location measurements to upscale all this model-based data. And also what we would like to look at in the future is to the integration of maybe smart city sensor networks, because we think there is a very big potential to incorporate this into these heat stress assessments. Yeah, and in general, we would like to really develop and offer planning, monitoring tools for climate change adaptation, green space planning, and public health alerts. And yeah, that's currently our status, and we would really like to discuss with you if you have any ideas or whatever. So I think on the next slide, we have also a little outlook on our webinar series. Maybe if you're interested in the general scope of these webinar series, we have some previous webinars available on YouTube. Actually, the recordings are there on a single tree detection with open geodata, or an analysis on parking spaces or forest monitoring that we are doing with Sentinel-2 data, as well as the detection of sealage or sealing impervious surfaces for water management. And if you're interested, we would be really happy to just invite you to the next upcoming webinar in February, because we are doing this monthly, and this will introduce our AI-based surface classification, surface cover classification from aerial imagery. Yeah, we hope there was something useful for you today. And if you have any questions, we would be very happy to discuss with you right now if you want. Or there are our contact email address, info@mundialis. You can always reach us. You can find more information on our webpage, or just talk to us. We would be very happy. Yeah, thank you very much.